Welcome to this video on stress calculations in the WellCAD Geomechanics workspace. We start with this borehole document with bit size, caliper, gamma ray, resistivity, compression and shear sonic velocities, porosities, RHOB, from which we have deterministic values. We also have the LOT or Lickhoff test. We have the MDTs, which are a specific type of RFT or repeat formation testing. And we have the mud pressure curve. This is a dataset that we can use for a post-mortem analysis. That's why we have the mud pressure curve, which was used in the perforations as shown in this dashed line. And this is just a display of the dataset. In order to start a new stress calculation in WellCAD, we need to select the Geomechanics workspace landing site. For the depth reference, in this case we have a TBD, so we will select TBD as a depth reference. For the borehole type, it is an offshore well where we have a 1,500 meters of water column and an air gap of 25 meters. We can use this operation as a proxy, as we also have a litho log which we could use, but we're not going to use it in this example just because we want to show how things work from the scratch. So we have all the different stress calculations available in WellCAD here, called the pore pressure and stress analyses. The parameters that we can calculate are the hydrostatic pressure, the vertical stress, the shale indicator, and the pore pressure. The pore pressure calculation is calculated in 3 stages. The first stage is the clear indicator. The second stage is the normal compaction trend calculation, or NTC. For the NTC, we can use the slowness or the resistivity, and then we can finally calculate the pore pressure. The reason we need the shale indicator and the NTC is because we use the Eaton's equation. The Eaton's equation needs the normal compaction trend line based on shales. Now we can calculate the minimum horizontal stress and the maximum horizontal stress. So let us just start from scratch and concentrate on the hydrostatic pressure first. We select it from the window and press OK. And now we have our Geomechanics workspace being built for us, with a new track on the right for the hydrostatic pressure. We will use the raw data and select a specific dataset that we can use in this stress calculation workflow. We select all the different logs required and we drag and drop them into the Geomechanics workspace. We recognize the display. In addition, we bring in the litho log. It is a very long length of almost 4,100 meters. There are different sections in this well bore and different casing points. We can see the whole well, and we can see that most of our data set is concentrated at the lower section of the borehole. And that's where we want to focus. But for the first calculation of the hydrostatic pressure, we are going to use the whole length of the well. We arrange the log display and make all the tracks the same size. We are going to work on the hydrostatic pressure. We have our hydrostatic pressure log, which is split into 2. This is the first 1,500 meters that determines the water depth or the water column. For the water column, we are going to use a density of 1.05 and we assign the TBD as the control depth. We are now going to add the MDT to the workspace and use it as control points in the hydrostatic pressure track. we can make them both on the same scale and with the same units. For the fluid density in the lower part, we set it to 1.05. We can see that the hydrostatic pressure fits very nicely with the control points. And that's how we calculate the hydrostatic pressure. Now we move into the next item. The calculation of the vertical stress. We have a new track on the right. To calculate vertical stress, we require density values. The problem is that for this specific wellbore, we only have reliable density values in the lower section of this well. And this is not enough to cover the thousands of meters that we have in the upper section of this borehole. This takes us to the next functionality, which is the use of the combine or composite curve for the density. To do this, we go to the parameter view and we see that we have in this section on the top for density and velocity estimation. We select density estimations and press OK. And now we have a new track deployed to the right. We can assign a zonation at 1500 meters of water depth by copying it from the hydrostatic pressure. And now we can see that we need to use the density and now we can see here that we need to use the density curve for the lower section of the combined density estimated curve, so we add a new zonation. We can zoom in a bit more to have more control on the top and the bottom of this zonation. And here in this zone we select the standard log method and we select the density log curve. We unselect the auto scaling and set a scale from 0 to 3. So this curve over here is exactly the same as the curve over there. We can also see that there is this DTCO curve that includes 400 meters of data. We create a new zone and we can use a new empirical equation to estimate density from sonic. For that we use the Gardner equation and press OK. We select the DTCO for the P slowness and that gives us the estimation for this zone. Now we have a big problem in the rest of the borehole, which is the lack of data from 3,400 meters to the top of the hole. So in this situation, WellCAD allows you to extrapolate the density of the seawater, which is a constant value, the same as that we had before, which is 1.05. But we have an issue here in this specific zone. We know we have rocks, and we can of course assign different densities for each of these rocks. If not, we can use another method, which is the extrapolation method. In WellCAD we have two methods, the polynomial and the linear method. The linear method will give us a straight line to the density at the top. The density at the top can be constrained at 1.05, which we have already. But the slope is incorrect. We know that the rocks will not behave like that. We will have decreasing density as we go to the top, but that's not that drastic. So maybe what we can do is to increase the density let's say to 2.3. No, let's put 2.0. And yes, there's a huge gap between the water density and the density of the rocks at this depth. We can always check the polynomial. And what the polynomial does is to look for the trend that exists in the backward depth. Let's start with 200 meters and try 300 meters, and it gives us different shapes depending on the different data sets. We put 250 meters, which is very similar to the linear extrapolation for this specific scenario. We can leave it like that. We can also correct the air density that we have at the top. And that will be another constant value for the air density. Let's put 0.0001, and that gives us our density estimated curve. As you can see, the workflow enables the possibility of different combinations of estimations of density. We zoom out, and now the next step is to use the density estimated curve in the overburden pressure calculation. We select this track and use the TVD curve as a reference. We select the density estimated curve that was just calculated, and we change the units to PSI. We change the color to visualize it better. We don't want the auto scaling, and we set the scale to 0 to 12,000. That's how our vertical stress curve looks like. Now we can move the hydrostatic pressure and the overburden pressure curves into the borehole view, because these two curves will allow us to see the envelope of the stresses. We go to export and select the two curves and press OK. We move the positions of the curves and change the color. Now we have a hydrostatic pressure here, and we have a vertical or overburden stress here. We will use the LOT here, and that will be the SH mean value. Now we go to the next step, which is the shale indicator, normal compaction trend lines, and pore pressure. These are the three steps for the pore pressure. We can select them at the same time, and they will be displayed on the right. We display the MDT in the same track as the pore pressure. Now we continue with the calculation of the pore pressure. We use the Eaton method for calculating pore pressure. There are two options: the Eaton equation using the sonic and the Eaton equation using resistivity. For both equations, we need to calculate the normal compaction trend line based on the distribution of shales in the subsurface, and the application of the equation will only be in the shales. So we need a threshold to differentiate the rocks which are shales and the rocks which are not. So the first step is to identify which are shales and which are not. We go to the shale track, and it will ask us for an input. The input can be any shale indicator, and in this specific case we have gamma ray as a shale indicator, and that is selected. Now we have the gamma ray here in the track, and we will try to separate the shale from the non-shale using the threshold as seen as a green dashed line. This will give us 2, 3, 4 big packages of shales. But as you can see high up, there is a change in the regime of the rocks. So we will create another zonation so that we can put a different threshold for the shales. We can zone into the area of investigation, which is the lower section of the borehole where we have more data. And we can be more specific with this threshold, moving it a little bit to the left, around 87 API of the gamma ray. Once we're satisfied with this calibration, we go to the next step, which is the normal compaction trend line in WellCat. We have two possibilities to deliver the normal compaction trend line. One is using the sonic as a proxy for the calculation of the normal compaction trend line, or the other is the resistivity. In this dataset, we have both. We have the compressional, which is the blue line, and we have the resistivity, which is the other. The deep resistivity in this data has a longer depth range, and it gives us a more complete pore pressure, but we will use both. So let us start with the normal compaction trend using the sonic. We have to select the proxy curve, which is the DTCO for the shale indicator we just calculated. This gives us the light blue line representing the calculated normal compaction trend, which is automatically fitted to this thick package of shales. It also shows all the brown dots indicating the shales. You can see these large zonations, and they are the non-shale or sandy parts of the formation, which are excluded from the calculation. But in this case, some points were included in the calculation as there were shale layers in the sandstone. We will now create a new zonation, but only for the range of the DTCO. We can also interactively modify the normal compaction trend line if necessary. We can put it like this so that we can cover the lowest shale package. The next step will be the normal compaction trend using the resistivity. We select the deep resistivity and the shale indicator, and we end up with this new curve. When we zoom out, we see the complete distribution of the normal compaction trend line. The trend line is quite easy to pick, and WellCat is doing it interactively for us. We can test how the automatic calibration works. We bring in this new zonation, and once we are satisfied with the normal compaction trend line, we can move to the pore pressure. So let us focus on the pore pressure curve and look at the lower section first, where we have some deterministic values that will give us further control on the output. We select this interval and we can assign the input that controls the Eaton equation using the sonic log. The units will be in PSI for consistency, and the scale from 0 to 12,000, the same scale as the MDT. And we select the DTCO, the normal compaction trend line. The NTS in this case indicates the shale indicator and the overburden pressure, or the vertical stress that we calculated before. And we select the hydrostatic gradient that we calculated before. And this exponent has to be manually calibrated by the user. For shales of this type, 3 is probably too high, So we put in 1.5, and as we can see, the curve is recalculated. We can see that these MDT control points are a bit low and the curve values are a bit high. So we go back to our previous interpretations. There's always going to be some interactive usage every time we change the threshold of the shales and when we change the normal compaction trend slope. This will affect the output of the pore pressure. So for instance, if we are more drastic in our changes and move the shale cutoff, the calculated pore pressures will be changed interactively. So let's give the pore pressure a thicker line so we can see it better. When we modify the normal compaction trend curve, because we want to be more drastic with the shales, we can see that they move and the pore pressure changes. So once the user is satisfied with these calculations, they can move it to the borehole viewer. And in this specific scenario, because we have deep resistivity, we add a zonation by copying it from the NTCR. Now we have a combined pore pressure curve. We move the zonation boundary a bit lower. And now we have this upper section. We can select the Eaton resistivity method. We zoom out so we can see more of the depth range. And then we select the RSD here and the NTC from the resistivity. We select the shale indicator, which is 30 here. We do not want to interpolate where we don't have data like this in this sandy parts, so we have gaps. And we keep the pore pressure curve that we calculated. We can do, of course, a better job with different zonations if we target them individually. Naturally, WorldCAD allows us for that as we add these zonations. Once the user is satisfied with the output for the pore pressure, they can export it. Once we make sure it is selected, press OK and go to the borehole view. Now we can see the pore pressure that we calculated, which is put into context, and we can see how it looks like. There are some gaps that probably need to be corrected, which we can do later. So the calculations have been performed for the pore pressure in these intervals where we had MDT data such as here and here, and this is the resulting curve. We can continue with the geomechanics process for the calculation of the SH-min and the SH-max, which are the minimum and maximum stresses. We create more space by hiding a few tracks from the display. Now we select the parameter view, and we can select the minimum and maximum horizontal stress that are both going to be calculated at the same time. So now we will have two new tracks deployed to the right of the display. Now we can add zonation here in the lower section where the calculations are going to take place. And we copy the zonation to the SH-max. We're going to start with the parameterization process, which requires the vertical pressure, which is the overburden pressure that we calculated before, the pore pressure, which is the PP underscore edited, and the Young's modulus and the Poisson ratio. We can calculate them in the Rock Mechanics workspace, but in this case we bring them in from the borehole view. We select the biot, the Young's modulus E underscore dyn, the Poisson ratio, and drag and drop them into the geomechanics workspace. Then we're going to continue with the parameterization process. We select the Young's modulus, the Poisson ratio, and the biot. We want the output in PSI, so we unselect the auto scaling and set the scale from 0 to 12,000 as in the other calculations. We also need to enter the minimum and maximum values for the strain. So for the minimum, we can consider that we are in a passive margin tectonic stress. So we entered this for the minimum value, and for the maximum value we enter this value. And that will be the output that we get. In this case, we also have a leak-off test, or LOT, which we can bring into the geomechanics workspace and use it as a control point. It is a leak-off test obtained at the top of the section or at the base of the casing. We move it to the SHMIN track. And if both curves are very close or coinciding, we've done a good job. Indeed, we are doing a very good job, as you can see. Now we can continue with the SHMAX calculation. For the vertical pressure, we select the overburden pressure, the pore pressure, Young's modulus, Poisson ratio, biot, and the minimum and maximum strain. For the units, we select PSI, and the scale is 0 to 12,000. So once we're happy with the output of the SHMIN, SHMAX, we export them to the borehole view. We display the output alongside the other stresses. We change the color of the curves, and this is how we calculate all the stresses in WELCAD. Thank you for watching, and we look forward to seeing you in other videos.